welcome to the second edition of Currylif VSSP. So Currylif is a alumni association of MTTS, and as we do student seminars in MTTS program, we have decided to from last year we have decided to do this online also, and this is the first session of the second edition. Yeah, I would like to call Mr. Soumya De, who is a postdoctoral fellow at CMI, to say something about MTTS as we know it. He's more qualified.
Yeah, first of all, Shreyas, your audio was not very clear, I think. So, yeah. So what you tried to say is like, what is Currylif? So I'll repeat. Currylif is basically a team of students, and basically they're students of MTTS and they're organizing several events like talks or seminars by students, VSSP like this, and soon we'll have this Currylif Days 2022. So yeah, that's basically about Currylif, and I think we can begin, right? So today we have 3 speakers for VSSP, and the first speaker is Prapti. She has done level O this year of MTTS. She's from St. Xavier's College, Ahmedabad, and she will be talking about dimension formula for sum of subspaces. Yeah. So over to you, Prapti. You can start.
Okay. Good afternoon, everyone. Myself, Tala Prapti, and today's my seminar topic is dimension formula for sum of subspaces. This is the very important topic in linear algebra. So let's start. Okay. My session plan is some basic examples of Bayes extension theorem, examples of dimension formula for sum of subspaces to relate with the theorem. Then I will be giving some statement of the theorem, some geometrical interpretation, strategy of the proof, and at last I will stop my session with a concluding sentence about can we extend the dimension formula for sum of subspaces. Okay. Let's consider some examples. Suppose my vector space V is R2 and W is a subspace of a vector space V where W is x-axis. So my W will look like x comma 0 such that x belongs to R. Okay, so a basic question arises that what are the bases of vector space V? So as V is R2, the vector spaces of V, standard vector spaces, can someone? Yes. So we can think about standard vector spaces of V R2 as 1, 0 and 0, 1. Okay, as V is my vector space R2, so dimension of V will be 2. W is a subspace of vector space V, which is x-axis. So it's just a line. So bases of W will be k, 0, such that k belongs to R. Or basis itself is by k, 0. Since W is x-axis, dimension of W will be 1. So the question arises that can I extend the basis of W to a basis of vector space V? That is, my basis of W is just this. And can I add some vector of R2 in W set such that the two vectors are linearly independent and it spans the vector space V, which is R2? The answer to the question is yes, we can extend. If I add k, 0 with some another vector of R2 as 0, 1. So we can see that these two vectors are linearly independent and it spans the vector space V, which is R2. So yes, the answer is yes. We can extend the basis of W to the basis of vector space V by adding some vectors in the basis of W such that the vectors are linearly independent and it spans the vector space V, which is R2. Let's consider some similar examples. Let's suppose V is my R3 and W is a subspace of a vector space V where W is equal to XY plane. So obviously my W set will have all the elements as X, Y, 0 such that X, Y belongs to R. As V is R3, let's consider some similar standard bases of R3 as 1, 0, 0, 0, 0, 1, 0, 0, 0, 1. And similarly, V is R3, so dimension of V will be 3. Okay. What are the bases of W? As W is a set of all the elements of XY plane. So the basis of W will be X, 0, 0, 0, Y, 0. Okay. In the basis of W, there are only two elements.
So Prapti,
Yes,
what is X and Y?
sorry, sir.
What is X and Y?
Okay. X and Y are real numbers. We can take any real numbers from W is a basis set which consists of real numbers, and here I'm considering in W basis as X, 0, 0 and 0, Y, 0, where X and Y are real numbers. Any real
X
number.
be 0?
Sorry?
Can X be 0 or Y be 0?
Yes. X and Y cannot be 0. Because if I put X is equal to 0, my theta element will be in W. But if I put theta, then it is linearly dependent. So I want all the set of elements which are linearly independent sets. So my X and Y are not equal to 0. They can be other real numbers. Is this fine?
So you meant to write Y not equal to 0 and X not equal to 0.
Yes, sir. So dimension of W.
X can be equal to Y, right? You said.
Yes. Yes. Sorry, sir. It's X can equal to Y.
No, they may be, they may not be. So you need not write anything about that. You just remove that.
Okay, sir.
Yeah.
Since there are only two elements in basis of W, so they are linearly independent. So we can say that dimension of W are the number of elements in basis of W, which is equal to 2. Again, the same question. Can we extend the basis of W to a basis of V? That is, can I add some more vector here in this set, one more vector, such that this vector is linearly independent to all other vectors and it spans the vector space V, which is R3. Yes, the answer is again same. X, 0, 0, 0, Y, 0. And if I add a third vector as 0, 0, 1. So with the same conditions of X and Y, X is not equal to 0, Y is not equal to 0. So we can see this, all the three elements are linearly independent and it spans the vector space V, which is R3. So we can see that from both the examples, the basis of any subspace W of a vector space V can be extended to the basis of that vector space. So from these two examples, we can directly see that this is true. But is this true in general also? The answer is yes. This is true in general also, and this can be proved by a very well-known theorem known as Bayes extension theorem. So I will be just giving the statement. I will not go in the proof of this theorem. The Bayes extension theorem states, let V be a vector space of dimension n and let W be a subspace of vector space V. So the basis of subspace W are W1, W2 up to Wk, and this can be extended to the basis of vector space V, which are V1, V2 up to Vn, such that Vi is equal to Wi for 1 less than or equal to I less than or equal to K. So my subspace W consists of these all elements in its basis. Including these elements, I can add some more vectors to this, and I can get the basis of vector space V. So Here we are noting that we are considering all the vector spaces which are having finite dimensions only. We are not looking upon the cases where V is having infinite dimensions. Okay. Now let's talk about some relations between the dimension of W1 plus W2, dimension of W1, dimension of W2, and dimension of W1 intersection W2. Let's think about some examples. Like suppose V is a vector space having, which is R3, and W1 and W2 are subspaces of vector space V, where my W1 is x-axis and W2 is xy plane. So since W1 is x-axis, all the elements of W1 will be in the form of x comma 0 comma 0, such that x belongs to R. And W2 is my xy plane. So we know that in xy plane z is 0. So all the elements in W2 will be alpha comma beta comma 0, such that alpha comma beta belongs to R. The question is, what is W1 plus W2? Okay, W1 plus W2 will be a set having elements as small w1 plus w2, such that w1 belongs to capital W1, w2 belongs to capital W2. Okay, so in a general form, I can write W1 plus W2 as x plus alpha beta 0, such that x beta alpha belongs to R. So I can see that in all the elements of W1 plus W2 also look like all the elements of XY plane only. So my W1 plus W2 are the elements, consist of all the elements of XY plane only. So W1 plus W2 is XY plane itself. Now, what about W1 intersection W2? That is the intersection of line x-axis and the y is equal to x plane, xy plane. So the intersection is itself x-axis. Okay. Now let's talk about dimensions. So dimension of W1. Since W1 is x-axis, it's just a line. So dimension of a line is 1. Dimension of W2, that is xy plane, it's a plane, so its dimension is 2. Dimension of W1 intersection W2. W1 intersection W2 is x-axis, so its dimension is 1. Dimension of W1 plus W2. Now my W1 plus W2 is my xy plane. It's a plane, so its dimension is 2. Now, can we relate some relation between dimension of W1 plus W2 is equal to something, by addition I'm getting 2. What can be written here such that I will get the dimension of W1 plus W2? Any guess? With the help of dimension of W1, W2 and dimension of W1 intersection W2.
Ma'am, I think dimension of W1 plus dimension of W2.
Sorry?
Ma'am, I think dimension of W1 plus W2, dimension of W1 plus dimension of W2.
Yes. Yes. If I want to in LHS, I can apply something like 1 plus 2 minus 1, like this. We can do anything. Let's suppose this is true, because 1 and minus 1 cancels and I will get 2 is equal to 2, where 1 is dimension of W1, 2 is dimension of W2, and again 1 is dimension of W1 intersection W2. We'll see some other examples also. Okay, next example. Suppose V is R3, W1, W2 are subspaces of vector space V, where W1 is x-axis, W2 is yz plane. Since W1 is x-axis, again, same, all elements of W1 will be x belongs to R, and W2 is yz plane. So elements of W2 will be 0, y, z, such that y, z belongs to R. Again, the same question. What is W1 plus W2? Yes, anyone?
R3.
Yes. W1 plus W2 will be x, y, z, such that x comma y comma z belongs to R. So this is the my vector space itself V, which is R3, right? Now W1 intersection W2, that is the intersection of x-axis and yz plane. So intersection of x-axis and yz plane will be my theta. Okay. Dimension of W1, that is dimension of x-axis, it's 1. Dimension of W2, that is yz plane, it's a plane, it's 2. Dimension of W1 intersection W2. Now dimension of theta is 0. And W1 plus W2 is my R3. So its dimension is 3. Again, the same question. Can we relate something, some equality like dimension of W1 plus W2 is equal to something. Here my dimension of W1 plus W2 is 3. So with the help of dimension of W1, W2 and W1 intersection W2, what can be the equation? How can we equate to get 3?
Dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2.
Yes. We can think it's 3 is equal to 1 plus 2. This is 0. So it's equal. So in example 1 and 2, we can see something like relation between dimension of W1 plus W2 as dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. But is this true in general also? Yes, this is true. This can be proved by the theorem, which is my topic, dimension formula for sum of subspaces. The statement says, let V be a vector space and W1 and W2 be subspaces of vector space V. Then the statement says dimension of W1 plus W2 is equal to dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. We note that if W1 and W2 are subspaces, then W1 plus W2 are also subspace of is also a subspace of V, and W1 intersection W2 is also a subspace of V. So let's start the proof. If we know that W1 intersection W2 is a subset of W1. W1 intersection W2 is also a subset of W2. Okay. If W1 and the intersection W2 is a subspace of V, so again it will have some basis. Let's name the basis of W1 intersection W2 as U1, U2 up to UK are the basis of W1 intersection W2. And since W1 intersection W2 is a subset of W1, by the previous theorem, we can say that we can extend the basis of W1 intersection W2 to the basis of subspace W1. That is, I need to add some elements in this basis of W1 intersection W2 such that all the added elements and the remaining elements are linearly independent and it spans the subspace W1. So I add elements as U1, U2, UK, V1, V2 up to Vn for the basis of W1. Similarly, I can extend the basis of W1 intersection W2 to the basis of W2 by adding vectors W1, W2 up to Wn. Okay. Now, what I need to prove is, let's start from RHS side. My RHS says dimension of W1 plus dimension of W2 minus dimension of W1 intersection W2. So from here, I can say that number of elements in W1 which are linearly independent and spans W1 are K plus M. In W2, the number of elements are K plus N. And the number of elements in the basis of W1 intersection W2 are K. So here by filling all the values, we'll be getting M plus K plus N plus K minus K. So it will be M plus N plus K. That is my dimension of W1 plus W2 should be this. So what the number of elements in the basis of W1 plus W2 is equal to the dimension of W1 plus W2. So what I need to prove is my number of elements in basis of W1 plus W2 should be M plus N plus K. So first of all, let's claim that U1, U2 up to UK, V1, V2 up to Vm, W1, W2 up to Wn are the basis of W1 plus W2. Let's suppose this is my claim that number of elements in W1 plus W2 are here. These are K, these are M, and these are N. So K plus M plus N are the number of elements in basis of W1 plus W2. Let's start. Let's suppose any element belongs to W1 plus W2. So we can say that X is equal to small w1 plus w2, where small w1 belongs to a subspace w1 and small w2 belongs to subspace w2. Since w1 belongs to w1, since w1 has all the elements of bases as u1 u2 up to uk, v1 v2 up to vm. So small w1 can be expressed as span of these elements, like w1 is equal to summation alpha I ui, I is equal to 1 to up to k, plus summation beta j vj, j is equal to 1 to up to m. Similarly, w2 is an element of subspace w2, and as basis elements of w2 are u1 up to uk, w1 w2 up to wn, so it can be written in the span of this element. So w2 is summation gamma I ui, I is equal to 1 to up to k, plus summation delta j wj, j is equal to 1 to up to n, and x is w1 plus w2. So adding these two equations, I will be getting my x as summation alpha I plus gamma I ui plus summation beta j vj plus summation delta j wj. Seeing this equation, I can say that x is written by the summation, by the spanning of all ui's, vj's, and wj's. So from this equation, I can say that u1, u2 up to uk, v1, v2 up to vm, w1, w2 up to wn spans w1 plus w2, because I have taken x as arbitrary element of w1 plus w2. So now what I need to show is, I have already proved that this all elements spans w1 plus w2. The next thing I need to prove for basis of w1 plus w2 is the linearly independent, that all these vectors are linearly independent. For this, the condition should be, assume that alpha I ui plus summation beta j vj plus summation gamma r wr is equal to 0. And what I need to prove is, for linearly independent, that all alpha i's, all beta j's, and all gamma r's are equal to 0. From this equation, I came here, summation alpha I ui plus summation beta j uj, and this I took on RHS. So it will be minus summation r is equal to 1 to up to n gamma r wr. Okay. From here, the expression on the right hand side, this is summation r is equal to 1 to up to n gamma r wr. Since wr's are all the elements in the basis of w2, so this all the elements of w2 can be written by spanning of these elements. If I suppose all the coefficients of u1 u2 up to uk are 0 and summation gamma r wr, then this element will be in the element of w2. This belongs to w2. And on the LHS, summation alpha I ui, summation beta j vj, ui's, and v1, v2 up to vm are all the elements of w1. So by the spanning of this, I will get an element in subspace w1, right? So my LHS belongs to w1. As my LHS belongs to w1, RHS belongs to w2. So all the elements will be included in w1 intersection w2, right? The expression on the right side is an element of w2, and that on the left side lies in w1. Thus, summation minus r is equal minus summation r is equal to 1 to up to n gamma r wr belongs to w1 intersection w2. Any element belongs to w1 intersection w2 will have its will look like the span of the basis of w1 intersection w2. So what is my basis elements in W1 intersection W2. The elements are U1, U2 up to UK. So as this element belongs to W1 intersection W2, this will be an element of the span of this set U1, U2 up to UK. So it will look like summation J is equal to 1 to up to K alpha J Uj. So that if I take this equation, just a minute. If I take this equation, negative sign to the right hand side, I will be getting summation J is equal to 1 to up to K alpha J Uj plus summation R is equal to 1 to up to N gamma R WR. Okay, now we can see this all U1, U2 up to UK, W1, W2 up to Wn are basis elements of W2. Since all the elements are in the basis of W2, we can say that they all are linearly independent. So we can conclude that all alpha J's are 0 and all gamma R's are 0 for all J and R. So from here we can say that all gamma R's are 0. So let's put this in the main equation here. Here, if I put all gamma R, all the values of gamma R as 0, so I will be getting on LHS as summation alpha I ui plus summation beta j vj is equal to 0 here. So again, now LHS side is summation alpha I ui plus summation beta j vj. So here all the elements are elements of basis of W1 as U1, U2 up to UK, V1, V2 up to Vm are elements in basis of W1. As these are elements of basis, they are linearly independent. So we can conclude that all alpha i's and all beta j's are 0. From here, we concluded all gamma r's are 0. And here all alpha I and beta i's are 0. So we can directly say that this is 0. So this completes our proof. As already we have said that this all these elements spans my W1 plus W2. And at last, I need to show that they are linearly independent sets. So what I need to show, alpha i's, beta j's, and gamma r's are all equal to 0. And we have proved this. Hence, we have completed the proof. Okay.
Yeah. Prapti, you have something more to say? Because it's already more than 20 minutes.
Yes, sir. Last point is left to say.
Okay. Yeah, please finish.
Okay. We can see this, the dimension of formula, this. Can anyone guess, have you seen this formula ever before also? Like this similar type of formula for dimensions, have you seen this type of formula anywhere else also?
In sets, cardinalities of A union B.
Yes, yes. We have seen this type of similar formula in set operations for cardinality of A union B. What this says that in set operations, if I have two sets which are finite, namely as A and B, then number of elements in A union B is equal to number of elements in A plus number of elements in B minus number of elements in A intersection B. We are having the similar formula for dimensions of W1 plus W2. But can we extend? In set operations, we are also having that if we are having three sets, A, B, and C, which are finite sets, then according to set operations, we are having cardinality of A union B union C, we are having this formula. So can we extend this type of operation for some of all the three subspaces of vector space V, that is for dimension of W1 plus W2 plus W3? Can we say this formula is true? Any guess? Because if this is true, then we have to prove this. And if it is not true, we need to show some counter examples. Okay, here is one counter example to disapprove this statement. So let's try to finish it. V is my R2, W1 is x-axis, W2 is y-axis, and W3 is my y is equal to x line. So W1 dimension is 1, it's single line. W2 is also dimension 1. Dimension of W3 is also 1. Now, what is W1 plus W2 plus W3? the addition of x-axis, y-axis, and y is equal to x line will give me the whole vector space V is equal to R2. W1 intersection W2, that is intersection of x-axis and y-axis in my theta. Intersection of y-axis and y is equal to x line is again theta. X-axis and y is equal to x line, again it's theta. And W1 intersection W2 intersection W3, okay, W1 intersection W2 intersection W3 is again my theta. And so dimension of W1 intersection W2 intersection W3 is 0 since it's theta. W1 intersection W2 dimension is also 0. Similarly here also all are 0. So proving for applying this theorem, let's think dimension of W1 plus W2 plus W3, that is R2. Dimension of R2 is 2. This is my LHS. Whereas on RHS, dimension of W1, which is x-axis, is 1. Dimension of W2 y-axis is 1. And dimension of W3, that is y is equal to x line, it's again 1. And here all the values are 0. So on RHS, I'm getting 3. Whereas in LHS, the answer is true. So we can directly say that the dimension formula for sum of subspaces cannot be extended for more than 2 subspaces. It is only valid for sum of 2 subspaces. So that's all from my side, sir. Thank you.
Yeah, nice talk, Prapti. Any questions from the participants? You can unmute and ask. All right. If there is no question, let us thank the speaker. Yeah, you can virtually clap